Welcome, curious minds, to another deep dive. Today, we're plunging into a fascinating corner of history, one that, well, directly challenges a common narrative you might have heard. Imagine, if you will, a sort of romanticized medieval era. Gallant knights, happy peasants, long, hot summers, vineyards stretching across England, even a fertile, warm Greenland. Sounds pretty idyllic, right?
It does, and that's the popular image, isn't it? The picture often painted of the medieval warm period.
Exactly. And it's often brought up to suggest that, well, humanity thrived in warmer climates. So the argument goes, if it was warm then and humans were doing just fine, maybe even great, why worry so much about warming now?
hmm That's the crux of it.
But here's where it gets really interesting. This is seemingly straightforward argument. It often overlooks some, let's say, crucial details and context.
A lot of context, actually.
And that is our mission today. We're going to unpack the complex, reciprocal relationship between climate and human civilization.
Using two pivotal historical climate intervals as our natural experiments.
Right. The medieval warm period, roughly 900 to 1300 CE,
Give or take.
and its climatic counterpart, the Little Ice Age, spanning from approximately 1300 to 1850 AD, a much longer period.
Indeed.
Our vision is to take a deep dive into the historical data. We want to explore how these climate shifts were reconstructed,
How do we even know about them?
what their true nature and regional variability actually were,
Because that's key, the regional part.
and their profound ecological, societal, economic, military, and cultural impacts. We'll be paying particular attention to European societies.
And specifically, the Dutch Republic. A really fascinating case study in resilience.
Definitely. But before we dive into these specific periods, there's a critical question, isn't there?
Absolutely. How do we even know the climate was like 1,000 years ago?
Yeah, I mean, we certainly didn't have thermometers dotted around the globe back then.
Not at all. Daniel Gabriel Fahrenheit. He invented what we'd consider the first modern thermometer, the mercury in glass one, in 1714.
And Celsius came decades later.
Right. And systematic, widespread direct temperature measurement. That began much, much later, really mid-19th century onwards.
So for understanding ancient temperatures, scientists have to rely on something else.
Exactly. They rely on what we call proxy data.
Proxy data.
These are essentially indirect measurements. Think of them as natural archives that have recorded climate information over vast periods.
Natural archives, like what?
Well, the NOAA archive, for instance, holds over 10,000 such data sets. It's incredible.
10,000. Wow. Okay, what kinds of things are we talking about? What are these natural archives?
We're talking about incredibly diverse sources. One of the most important, certainly one of the most famous, are ice cores.
Right, from places like Greenland or Antarctica.
Precisely. Imagine these vast ice sheets and glaciers just accumulating layers of snow year after year, millennia after millennia. Each layer gets compacted over time, forming this incredibly precise timeline, like pages in a history book made of ice.
And trapped within these ancient layers.
Incredible clues. Things like volcanic dust from past eruptions, tiny air bubbles, which are literally samples of ancient atmospheres.
Actual ancient air. That's amazing.
It really is. And crucially for temperature, certain chemical markers called isotopes.
Isotopes. Okay, that sounds very scientific. How does that work? How does this chemical magic tell us about past temperatures?
It's quite fascinating, actually. We primarily look at oxygen isotopes,
Hmm.
specifically the ratio between two types, oxygen-18 and oxygen-16.
Okay.
Now, oxygen-18 is slightly heavier than oxygen-16, just a tiny bit.
Right.
When water evaporates from the oceans, it takes a little bit more energy to lift those water molecules containing the heavier oxygen-18.
Okay, so the lighter ones evaporate more easily.
Essentially, yes. Then, as this moist air travels towards the poles, it cools down. As it cools, the water vapor condenses and falls as precipitation, rain, or snow. And the water molecules containing those heavier isotopes, they tend to condense and fall out first.
Ah, because they're heavier.
It's related to the energy states, but yeah, they're preferentially lost earlier in the journey. This means that by the time the water vapor reaches the polar ice sheets, especially during colder periods, it's become more depleted in that heavier oxygen-18.
So colder temperatures mean less oxygen-18 in the snow that forms the ice.
Exactly. The colder it gets, the more depleted the snow is in oxygen-18 compared to oxygen-16. By measuring this ratio, layer by layer, in the ice cores, scientists can reconstruct past temperatures with remarkable accuracy.
Are there complicating factors?
Oh, sure. Things like changes in ice sheet thickness, the extent of sea ice cover, even the isotopic composition of the oceans themselves can influence the relationship. But scientists have developed methods to account for these factors, calibrating the relationship, the delta-T relationship, as it's known to get reliable temperature readings.
And these ice cores, they can show even finer details, right? Like seasonal changes.
Yes, absolutely. Within the layers, you can often see distinct seasonal variations in the oxygen isotope levels. In the fresh snow, the firn that's the partially compacted snow, and then deep down in the ice itself.
So you can tell summer from winter in ice that's thousands of years old.
In many cases, yes. For example, looking at snow pits dug in central Greenland, just 10 meters deep can reveal about 20 years of seasonal variations. It allows for incredibly high-resolution climate reconstruction.
But I imagine interpreting the really old stuff gets tricky.
It can. While different ice cores, like the famous Gry and Giaisoki-2 cores from Greenland, generally show good agreement, especially for more recent millennia. When you get really deep into ice that's tens or hundreds of thousands of years old, the immense pressure can cause the layers to become disturbed or folded.
So the timeline gets warped.
Potentially. It means that interpreting the oldest data, say from the Eemian period around 125,000 years ago, requires really careful analysis and cross-referencing between different cores and proxies. There can be inconsistencies.
Makes sense. So beyond ice cores, what other proxy sources do scientists use to build this picture of past climates?
Another critical source is tree rings, dendrochronology.
Right, counting the rings. But it's more than just age, isn't it?
Much more. The width of each tree ring, representing 1 year's growth, provides an annually resolved measurement that reflects environmental conditions, including temperature and rainfall.
So thicker rings generally mean better growing conditions, warmer, perhaps.
Generally speaking, yes, though it depends on the tree species and what limits its growth in a particular region. We have these amazing millennium-long reconstructions from places like northern Scandinavia and the Alpine Arc in Europe. They use cores from living trees, cross-dating them with patterns found in dead wood lying on the ground, subsoil material preserved in bogs or lakes, and even timber used in historical buildings.
Wow, connecting living trees to ancient logs.
It builds a continuous timeline, providing this robust network of annual climate data going back centuries, even millennia.
Incredible. And what about the oceans and lakes? They must hold clues too, surely.
Oh, absolutely. Think about ocean and lake sediments. There are vast, vast archives. Billions of tons of sediment, dust, river runoff, biological material accumulate year after year on the beds of oceans and lakes.
Layer upon layer, like the ice cores.
Exactly. And trapped within these sediment layers are all sorts of tiny clues. Microfossils, for example, like the shells of tiny marine organisms called foraminifera.
Foraminifera, okay.
Their shell chemistry, particularly the isotopes within them, changes depending on the temperature and chemistry of the water they lived in. We can also find molecular fossils, like the waxy coatings from plant leaves that washed into the lake or ocean.
Leaf waxes, how do they help?
Their chemical structure can also reflect the climate conditions the plant grew in. Analyzing these microfossils and molecular fossils allows scientists to reconstruct climate information stretching back not just thousands but millions of years. Yes, ocean sediments provide some of our longest climate records. And even the physical properties of the sediment itself, its grain size, its shape, its structure, its color, can change with the climate, offering additional layers of information.
Okay, this all sounds incredibly robust, using all these different lines of evidence, but it also sounds really complex. Why is it so crucial, then, to combine information from multiple proxy sources? Why not just rely on, say, ice cores?
That's a critical thinking point, really, and something for you, the listener, to ponder. Why the need for multiple sources? It fundamentally comes down to building confidence and achieving robustness in the reconstructions.
Oh, okay.
Each type of proxy data has its own strengths, but also its own limitations and potential biases.
Right. Like ice cores are amazing for atmospheric composition and give great detail, but they're mostly limited to polar regions.
Exactly. And tree rings give you that fantastic annual resolution, but they're tied to specific tree species, specific regions, and might reflect rainfall more than temperature in some areas.
And the sediments give you those super long timelines.
But often at a lower resolution, meaning you might lose some of the year-to-year detail. And they reflect conditions in the water or the surrounding land.
So by combining them all.
By combining multiple independent proxy records from ice cores, tree rings, ocean and lake sediments, corals, speleothems, even historical written records where available scientists can cross-validate their findings. They can fill in geographical gaps, average out potential biases from any single record, and gain a much more comprehensive, reliable, and nuanced understanding of past global and regional climate variations.
It prevents you from drawing big conclusions based on potentially localized or incomplete data.
Precisely. It's about building the most complete and accurate picture possible from all the available evidence.
What a fantastic overview of how we actually peer back in time to understand Earth's climate. That really sets the stage. So with that foundation laid, let's dive into our first historical flashpoint. The medieval climate anomaly, or as it's more popularly known, the medieval warm period. Okay, so let's circle back to that common argument we kicked off with. The popular viewpoint that the medieval warm period existed, it was as warm or maybe even warmer than today, and crucially, that it was broadly a positive thing for humanity.
Right, the narrative of thriving medieval societies, those English vineyards, the fertile Greenland.
Yeah, sounds great. But as one source we looked at, debunking a climate myth, points out, there are some significant problems with taking that narrative at face value. It highlights three main issues.
Let's unpack those, starting with the first one.
All right, hit us with problem number one. How warm was it really?
This is key, because yes, hundreds, possibly thousands of studies have reconstructed temperatures during the MWP, roughly 900 to 1300 CE, and many of them do show temperatures comparable to, and in some specific cases perhaps warmer than, the late 20th century in certain regions.
Like central England and Western Europe, which often gets cited.
Exactly. Places where we have good proxy records often show distinct warming.
So that seems to support the argument, doesn't it?
It supports part of the argument, but the crucial nuance, the bit often left out, is its regional nature. The medieval warm period was not, and this is really important, a monolithic period of uniform global warming.
Ah, okay. So while parts of Europe and the North Atlantic were warming up,
Other regions around the globe were actually cooling, or saw little significant change, or experienced warmth at different times. It wasn't globally synchronous.
like a collection of regional heat waves maybe, rather than the whole planet having a fever?
That's a pretty good analogy, yes. It lacked the global uniformity we see in modern warming. And for broader context, it's also worth remembering that the highest global mean surface temperatures of the entire Holocene epoch, that's the last 11,700 years or so, likely occurred much earlier,
Earlier. When?
during what's sometimes called the Holocene climatic optimum, roughly 8,000 to 4,000 years ago. While there's some disagreement between different reconstructions on the exact timing and magnitude, most evidence suggests this earlier period was warmer globally than the MWP. So the MWP wasn't necessarily the warmest period even in recent Earth history on a global scale.
Okay, that definitely complicates the simple "it was warm" picture. So problem one, it wasn't globally uniform warmth. What about problem number two?
Problem two challenges the idea that it was broadly a good thing for humanity.
Right, that romanticized view of medieval life, the chivalry, the happy peasants drinking in the fields.
It conveniently ignores the harsh realities of the time, doesn't it? Like constant warfare, devastating plagues, incredibly high infant mortality. Life for most people was anything but idyllic.
True. The source points out that while some areas did see benefits, like those Viking settlements in Greenland being viable for a time, or vineyards growing further north in England.
These localized benefits were often outweighed by widespread societal problems and conflicts elsewhere. Climate stress, even during generally warmer periods, could be destabilizing.
Can you give us a few specific examples where climate adversity caused problems, maybe even around or during the MWP?
Certainly. History is full of them. We could look back even further to the Younger Dryas event, about 12,800 to 11,600 years ago.
That was a sudden cold snap, right?
A major one. A significant cooling, maybe 4 to 5 degrees Celsius quite rapidly in many places, likely triggered by freshwater release into the Atlantic, disrupting ocean currents. And the impacts were profound. It's linked to widespread hunger and conflict, particularly in sensitive regions like the Nile Valley. It even destabilized some of the earliest settled human communities, like the Natufians in the Levant.
So abrupt climate shifts, even cooling ones, were major disruptors.
Definitely. But we don't need to go back that far. Consider the collapse of the classic Maya civilization in Mesoamerica, mainly during the 8th to 10th century CE. This overlaps with the early part of the MWP timeframe.
Right, the Maya collapse is complex, attributed to many factors.
It is, but there's growing evidence, including direct chemical analysis of sediments from the Caribbean seabed, pointing to severe, prolonged regional droughts as a major contributing factor.
Droughts during a supposedly warm period.
Exactly. It highlights the regional variability. These studies indicate three major droughts, around 760, 800 CE, 840, 870 CE, and 890, 920 CE, likely due to a weakening of the summer monsoon system in that region.
So even as parts of Europe might have been enjoying milder conditions, the Maya region was suffering devastating droughts linked to climate shifts.
Precisely. It directly contradicts the idea of a universally good outcome from past climate variations. Regional climate adversity, whether too cold, too hot, too wet, or too dry, has consistently contributed to societal stress and destabilization.
Okay, so problem one, not globally warm. Problem two, not universally good. That brings us to problem number three, which you said was the most overlooked, but maybe the most important.
I think it is, especially when comparing the past to the present. Problem three is the rate of change.
The speed at which the climate shifted.
Exactly. Even in those regions that did experience significant warming during the MWP, the evidence suggests that the rate of temperature change was considerably slower than the rate of warming we are experiencing today.
How much slower?
We're talking about changes playing out over centuries, maybe even longer. This allowed past societies, ecosystems too, more time to adapt.
Time for gradual adjustments.
Yes, incremental changes in farming practices, shifting settlement patterns, developing new trade routes or resource management strategies, it wasn't instantaneous.
Whereas modern climate change
Is occurring at an unprecedented pace, compressing those adaptation timelines dramatically. We're seeing changes in decades that might have taken centuries in the past.
that makes a huge difference. It's not just how much it warms, but how fast.
It's absolutely critical. You can use the analogy of heating a pot of water. Slowly turning up the dial allows the water to heat gradually, dropping the pot directly onto a blazing hot stove. The effect is much more sudden and disruptive.
Right. The system, whether it's an ecosystem or a human society, has less time to cope with rapid change.
Precisely. Living systems, including our complex civilizations, are far more capable of adapting to gradual shifts than to rapid, abrupt ones. This faster rate of change today is a fundamental factor differentiating current climate concerns from many historical climatic fluctuations.
Okay, so those are three major problems with the simple, rosy view of the medieval warm period. To recap quickly, one, it wasn't uniformly global warmth, more like regional variations. Two, the impacts weren't universally positive. Many societies faced significant climate-related stress. And three, perhaps most crucially, the rate of change back then was much, much slower than today's warming.
That sums it up well. It paints a far more complex and nuanced picture than the simplified narrative often allows.
Absolutely. Now that we've challenged some prevailing narratives about the medieval warm period, let's shift our focus to the other side of that climatic coin. The period of cooling that followed, the Little Ice Age. Okay, so after the medieval warm period, or medieval climate anomaly as it's sometimes called, Europe and other parts of the world entered a cooler phase, the Little Ice Age.
That's right. The Little Ice Age, or LIA, is generally considered to have spanned roughly from 1300 to 1850 AD. Though, like the MWP, there's debate about the exact start and end dates, and some scholarship focuses on the coldest temperatures occurring more specifically between maybe 1400 and 1700 AD.
And was this a period of just uniform cold everywhere, or did it also have that regional variability we talked about with the MWP?
Good question. And no, it's important to clarify again. The LIA was not a monolithic period of uniform global cooling. It wasn't a true ice age in the geological sense.
Right, not like glaciers covering continents.
Not at all. Instead, it was characterized by a complex, sort of multi-phase nature. Its severity varied significantly across different geographical regions and over time within that broad period.
So how much cooler did it actually get?
Well, looking at the Northern Hemisphere average annual temperatures, the decline was approximately 0.6 degrees Celsius, which is about 1.1 degrees Fahrenheit, compared to the preceding centuries.
Okay, 0.6 C average drop. Doesn't sound enormous globally, but maybe more impactful regionally.
Exactly. Specific European areas experienced much more pronounced cold episodes. During these colder phases, regional temperatures could plummet by 1 to 2 degrees Celsius, that's 1.8 to 3.6 Fahrenheit, below the longer-term averages, and these cold spells could last for decades.
1 to 2 degrees regionally, that sounds much more significant, especially for agriculture and daily life.
It really was. Take the Maunder Minimum, for example. This was a particularly cold phase of the LIA, roughly 1645 to 1715, coinciding with a period of very low solar activity.
Right, fewer sunspots.
Fewer sunspots, less solar energy output. And during this time, European winter temperatures were reduced by a notable 1 to 1.5 degrees Celsius below the norm. That made winters significantly harsher.
A I can imagine. And what about the impact on farming seasons? You mentioned vineyards in England during the MWP. Did things reverse?
They certainly did in many places. The impact on growing seasons was quite severe across much of Europe. During the coldest years of another LIA cold phase, the Grindelwald fluctuation in the late 16th century, the growing season in many parts of Europe was reduced by as much as 6 weeks.
6 weeks. That's huge for farmers.
Absolutely devastating. It severely limited what could be grown and the reliability of harvests. There was also evidence for an overall increase in precipitation in areas like the Low Countries during the LIA.
So colder and wetter in some key agricultural regions.
It seems so. And some historical climatologists, like Hubert Lamb, argued that the frequency of severe gales and storms in the North Sea region rose sharply during the LIA minima. Early modern Dutch weather observers also recorded a surge in storminess during these cold periods.
Okay, so colder, sometimes wetter, shorter growing seasons, maybe more storms. What actually caused this shift into a colder climate? Was it just the sun going quiet?
The reduced solar activity, like during the modern minimum, was definitely a factor, but it wasn't the only one. The LIA seems to have been caused by a complex interplay of several natural phenomena.
Such as?
Well, alongside reduced solar activity, there was an increase in explosive volcanic eruptions.
How do volcanoes cause cooling?
Large eruptions inject massive amounts of aerosols, tiny particles, mostly sulfate compounds high in the atmosphere, into the stratosphere. These aerosols can stay up there for years, reflecting sunlight back into space and causing widespread, albeit temporary, cooling at the Earth's surface.
Ah, like a natural sunshade.
Exactly. We have historical examples like that massive eruption possibly in Rabaul near Papua New Guinea back in 535 CE. That's thought to have caused an approximate 3 degrees Celsius global cooling that lasted for maybe a decade.
Wow, 3 degrees from one eruption.
It was a huge event, and the records show widespread disruption, crop failures, hunger, social unrest across many parts of the world following it. So increased volcanic activity during the LIA likely contributed significantly to the cooling phases.
Okay, so low solar activity, more volcanic eruptions. Anything else?
Shifts in ocean circulation patterns are also thought to have played a role. Ocean currents are like massive conveyor belts distributing heat around the globe. Changes in these patterns, perhaps triggered by other factors, could alter regional and even hemispheric climates.
So a combination of factors pushing the system towards a cooler state.
Precisely. It wasn't one single cause, but likely a convergence of these natural drivers.
Now, that covers the natural side, but thinking back to our discussion on the MWP, this raises an important question again. Could there possibly have been any human influence, even an unintended one, on the Little Ice Age?
That's a really fascinating and more recent area of research. And yes, some scholarship does suggest a potential, albeit entirely unintended, anthropogenic influence.
Unintended human influence causing cooling. How?
It relates to the period after European contact with the Americas, starting in the late 15th and 16th centuries. The tragic consequence was the massive depopulation of indigenous peoples across the Americas due to disease, conflict, and societal collapse, often referred to as the Great Dying.
A terrible chapter in history.
Truly horrific. And one ecological consequence of this vast depopulation was that huge areas of previously cultivated land, managed landscapes, were abandoned. Nature reclaimed these areas, leading to widespread reforestation across the Americas. Millions upon millions of trees grew back.
And trees absorb carbon dioxide.
Exactly. This massive regrowth of forests likely sequestered a significant amount of carbon dioxide from the atmosphere over the 16th and 17th centuries.
CO2 being a greenhouse gas, so removing it would cause cooling?
That's the hypothesis, that this large-scale human-caused but unintended reforestation contributed, alongside the natural factors, to the global cooling trend observed during the LIA, particularly deepening the cold in the late 16th and 17th centuries.
Wow. So while modern climate change is driven by adding CO2 through industrial emissions, the LIA might have been partly influenced by removing CO2 through reforestation linked to colonization.
It's a compelling line of research, highlighting the complex and sometimes unexpected ways human activities can interact with the climate system even before the Industrial Revolution.
That's truly eye-opening, a very different kind of human impact.
Okay, so we have the drivers natural, maybe even unintentionally human.
Yeah.
Now let's explore the direct ecological consequences of the LIA. How did this changing climate directly impact Europe's environment, and particularly its agrarian foundations?
The ecological consequences were stark, immediate, and often devastating. They directly impacted the very basis of European societies, which were overwhelmingly agrarian at the time.
Like what, specifically? Well, for one, we saw widespread glacial advances in mountainous regions like the Alps, Scandinavia, and Iceland. Glaciers that had retreated during the MWP surged forward again, sometimes obliterating entire villages, farmlands, and pastures that lay in their path. There were historical accounts and geological evidence of this.
Settlements literally overrun by ice.
Yes, and in northern waters, there was significantly expanding sea ice. This severely disrupted vital trade routes, particularly in the Baltic Sea and around Iceland and Greenland. Navigation became perilous or impossible for much longer periods each year.
Cutting off trade and communication.
Exactly. And beyond the ice, Europe experienced these persistent meteorological anomalies we touched on. Consistently colder winters, significantly shorter growing seasons, and highly unpredictable extreme weather events, severe storms, unseasonal frosts, sometimes excessive rainfall or droughts in different regions at different times.
And these changes must have hit agriculture incredibly hard, leading to food shortages.
They absolutely did. These environmental shifts directly undermined Europe's agrarian foundations. The colder winters, shorter growing seasons, and unpredictable weather led to recurrent, widespread crop failures.
Which inevitably leads to
Famine. These crop failures caused recurrent, often devastating famines across the continent. A prime early example is the Great Famine of 1315-1317.
right at the beginning of the LIA period.
Yes, this famine was catastrophic, leading to millions of deaths across northern Europe. Estimates suggest maybe 5 to 12% of the population perished in some regions.
What caused it? Just the cold.
It was a brutal combination, triggered by unusually cold and wet conditions starting around 1315. It led to widespread crop failure, grain rotting in the fields, and severe livestock disease outbreaks as well. A perfect storm of agricultural disaster.
Millions dead. That's staggering.
It was. And even when famine wasn't raging, the consistent low crop productivity due to the climate meant general food shortages were common, leading to soaring food prices for basic necessities like grain. Sustenance became precarious for a large part of the population.
Did farmers try to adapt? Change what they grew?
They had to. There was often encouragement or just necessity, pushing farmers to abandon crops like wheat, which generally prefers warmer, drier conditions, and shift towards hardier, more cold weather tolerant crops like barley, oats, or rye. These could survive better in the shorter, cooler growing seasons.
We can actually see the economic impact in historical data, right?
Yes, economic historians have done fascinating work looking at historical records like grain yield ratios, how much grain was harvested for each unit sown. Their studies show a clear correlation. Warmer temperatures during the growing season significantly increase yield ratios, while colder growing seasons consistently meant lower yields. One study estimated a 1 standard deviation increase in growing season temperature boosted the yield ratio by over 10%.
So colder LIA growing seasons directly translated to less food per acre.
Precisely. And this agricultural impact had knock-on effects. Other studies have found that a larger fraction of cooler years was correlated with smaller city sizes in Europe. The negative effect seems to have been driven especially by those particularly cold years, suggesting climate stress directly impacted urbanization and economic activity.
Wow. Okay, so the Little Ice Age. A regionally variable period of significant cooling lasting centuries, driven by a complex mix of natural factors, solar activity, volcanoes, ocean currents, and maybe even unintended human influence via reforestation in the Americas.
Its ecological impacts were severe. Glaciers advancing, sea ice expanding, growing seasons shrinking, extreme weather increasing.
All directly undermining agriculture, leading to devastating famines like the Great Famine, chronic food shortages, and rising prices. It clearly presented immense challenges.
Immense. The very foundations of society were shaken.
Let's move on then and explore how societies actually responded to this profound shift. Did they just collapse, or did they find ways to cope? #, societal upheaval and adaptation in the face of cold. The LIA conditions undermining agriculture, creating food scarcity. They must have posed profound challenges reaching far beyond just farming. What were the broader societal repercussions?
Oh, absolutely. The societal repercussions were equally profound, if not more so. They affected everything from population dynamics and disease outbreaks to political stability and social structures.
How did it affect population numbers?
Well, population dynamics were severely impacted, primarily through increased mortality rates. The famines obviously played a direct role, but also famine-induced malnutrition weakened populations, making them much more susceptible to epidemic diseases.
Right, weakened immune systems.
Exactly. When people are chronically undernourished, their bodies are less able to fight off infections. So malnutrition acted as a grim partner to disease.
This sounds like a recipe for widespread epidemics. Did the LIA contribute to major disease outbreaks? We often hear about the Black Death around this time.
Absolutely. The period saw major disease outbreaks, and they were often intricately linked in complex ways to the climatic conditions and their consequences. The most infamous example, of course, is the Black Death, the bubonic plague pandemic that swept across Eurasia and North Africa in the mid-1300s.
Which killed, what was it, a third of Europe's population? More?
Estimates vary, but it was staggering. Perhaps 30 to 60% of Europe's population perished. Globally, maybe 75 to 200 million people died. It's almost incomprehensible.
And how did the LIA's climate play into that horror?
It's complex, and plague is ultimately caused by the bacterium Yersinia pestis, spread by fleas on rodents. But the prevailing conditions likely created a fertile grounds for the pandemic. Factors like the poor harvests and food scarcity leading up to the 1340s, linked to the earlier LIA cooling and instability, meant populations were already stressed and potentially malnourished. There's also fascinating research looking further back at the plague's origins. Some studies suggest that climate fluctuations in Central Asia, the likely homeland of Yersinia pestis, might have played a role.
Oh, so.
Well, one line of thought connects earlier climate shifts. Perhaps a milder period around 1300 CE in the Himalayan foothills allowed wild rodent populations, the natural reservoir for the plague, to proliferate. Then subsequent cooling and perhaps increased rainfall or floods in the 1310s, 1330s could have stressed these rodent populations, causing die-offs or migrations, increasing the chances of the disease spilling over into human populations via fleas. Combined with factors like trade routes and conflict, it created pathways for the disease to spread rapidly.
Wow, so climate could affect the rodent hosts, the fleas, human susceptibility. It's all interconnected.
Very much so. And we see similar patterns with other outbreaks, even looking much earlier to the plague of Justinian in 542 CE, the first major bubonic plague pandemic.
That was much earlier, but you mentioned it coincided with that big volcanic eruption.
Exactly. It started in Constantinople and killed tens of millions across the Byzantine Empire and beyond. And it hit right after that massive volcanic eruption around 535 CE, caused significant global cooling, crop failures, hunger, and unrest. Again, a vulnerable population meeting a devastating disease in a period of climate disruption. Molecular genetics has actually confirmed that the Yersinia pestis strains from the 6th century, Justinian's plague, the 14th century Black Death, and later pandemics were all related.
So colder temperatures, climate disruption often seem linked to more disease. Is there ever a case where warmer temperatures also caused problems? Just to be balanced.
That's a really important point, yes. The direction of temperature change isn't the only factor. What matters most is the disruption from the usual climate that a region's agriculture and society are adapted to. Both warming and cooling, and changes in rainfall patterns, either excessive rain or drought, can severely affect food yields. Crops, livestock, pests, diseases, they're all attuned to a particular climate envelope.
So any major shift is disruptive.
Exactly. We have modern examples too. Think about the massive harvest losses in Russia during the extreme heat wave and drought in mid-2010, or the losses in Central and Western Europe during the 2003 heat wave. Those were due to very hot conditions causing crop failure. So they're about the instability and the departure from the norm, not just whether it's getting hotter or colder overall.
Got it. Okay, beyond famine and disease, how did this widespread environmental stress translate into political instability and social unrest?
The LIA acted as a powerful threat multiplier. It didn't necessarily cause conflicts or instability on its own, but it significantly intensified pre-existing social, economic, and political tensions.
How did it do that?
By creating resource scarcity, food, land, driving migration, increasing economic hardship, and generally making life more precarious. This fertile ground for discontent contributed to widespread social unrest, increases in vagrancy and crime, and likely exacerbated or prolonged major conflicts, like the brutal 30 Years' War in Europe, 1618 to 1648.
Can we point to specific examples where climate stress was a major factor in political collapse?
A particularly striking example comes from outside Europe: the collapse of the Ming Dynasty in China in the 1640s.
That was a huge event in Chinese history, linked to the LIA.
Directly linked, according to many historians and climate scientists. The collapse occurred during a period of extreme colder conditions in early 17th century China, coinciding with the Maunder minimum. Records show very cold summers and widespread severe drought plaguing China from the 1620s into the early 1640s. The drought from 1638 to 1641 was apparently China's most severe in half a millennium, hitting the critical rice-growing regions.
Leading to famine.
Massive famines, yes, as rice yields plummeted. This combined with other pressures Military failures, economic problems, social turbulence related to migration, even other weather disasters like major Yellow River floods created a powder keg. It fueled peasant rebellions, culminating in an uprising in 1644 that overthrew the Ming dynasty and allowed the Manchu conquest. It's a stark example of climate extremes contributing to state collapse.
A threat multiplier indeed. And then there's that really disturbing phenomenon we associate with this era. The witch hunts? Did the LIA climate also fuel that?
Yes, tragically it seems so. A particularly striking sociocultural consequence of the LIA's climate stress, especially during its colder phases, was the surge in systematic witch hunts across many parts of Europe.
When did this peak?
The persecution intensified during the 16th century and really peaked between about 1600 and 1618, coinciding with some very harsh climatic periods within the LIA.
And people literally blamed accused witches for the bad weather.
They absolutely did. Accused witches, overwhelmingly women, often poor or marginalized, were frequently blamed for causing inclement weather like hailstorms or unseasonal frosts, for destroying crops, making livestock sick, and even driving up grain prices through magic.
It sounds completely irrational to us now.
It reflects a desperate search for scapegoats in a time of immense hardship and fear, when scientific understanding of weather was limited. The bizarre and often destructive weather was interpreted by many as a sign of divine anger, or, increasingly, as the work of the devil acting through his human agents, the witches.
This really makes you think, doesn't it? It raises a question for you, the listener. How might a lack of scientific understanding of complex processes like climate lead to societal scapegoating and irrational responses during times of environmental crisis? Are there parallels we can see today, perhaps, in how blame is assigned for complex problems?
It's a sobering thought about human psychology under pressure.
Definitely. But despite all this, the famine, disease, unrest, witch hunts, European societies didn't just passively suffer and collapse, did they? They must have shown some resilience, some adaptation.
They absolutely did, and this is crucial. Despite the immense challenges, European societies demonstrated remarkable adaptive capacities. They weren't just victims, they were agents, finding ways to cope and even innovate.
So what does this all mean for how societies actually coped? What kind of ingenuity and resilience emerged during the Little Ice Age?
Well, we saw significant agricultural innovations emerge, driven by the need to cope with those shorter growing seasons and variable precipitation.
Like switching crops.
Yes, that shift from wheat to hardier grains like barley, oats, or rye was a key adaptation in many regions. But there were also innovations in land management, fertilization, and potentially new crop rotations designed to maximize yields under difficult conditions.
And what about trade? Did that help buffer the problems?
Hugely important. Another key adaptation was the expansion and intensification of trade networks. Since crop failures were often localized, one region might have a terrible harvest, while another did okay. Trade became essential for survival.
Moving food from surplus areas to deficit areas.
Exactly. Studies have shown that cities with better access to trade networks, particularly maritime trade, showed mitigated negative effects of temperature fluctuations on their size and prosperity. Being part of networks like the Hanseatic League, or having good access to ocean ports, provided a crucial buffer against localized food shortages. It increased overall resilience.
That makes perfect sense. If you can't grow it locally, you import it. But importing requires transport. How did transportation itself adapt to these new climatic realities, especially things like more sea ice or frozen rivers?
That's a great question, and it leads to some fascinating examples of adaptation, especially when we look closely at the Dutch Republic later. But even more broadly, climate stress acted as a powerful impetus for technological and organizational advancements in some sectors.
Like which ones?
The whaling industry is a prime example, particularly Arctic whaling, which really took off during the LIA.
Why whaling? More demand for oil.
Yes, Europe had a growing demand for oil for lighting, cooking, soap making, and whale blubber was a key source. But the expanding sea ice presented huge challenges, so whalers had to innovate. They developed new techniques to process the blubber, sometimes boiling it down right there on the ships or even out on the sea ice, rather than having to transport the raw blubber all the way back to port. Shipwrights also adapted, learning to grease and reinforce the hulls of whaling vessels to help them withstand collisions with ice and slide off thick floes.
Necessity driving innovation.
Exactly. And the expiration of some early corporate monopolies in whaling encouraged competition, further driving efficiency and innovation in ship design and hunting techniques.
Any other adaptations? Land use?
Yes. There's evidence that economies adjusted land use patterns according to comparative advantage. For example, in some areas, there might have been an expansion of cropland or pasture onto previously marginal loins to try and increase overall agricultural output in response to the climate-induced food stress. Data covering European countries from 1500 to 1850 shows these kinds of shifts in land use correlating with temperature changes.
So the key takeaway here is that climate stress, like the LIA, doesn't uniformly lead to decline or collapse.
Not at all. While it certainly caused immense suffering and hardship, it could also act as a catalyst, fostering innovation, adaptation, and the development of new economic opportunities for those societies that were able to respond flexibly and creatively.
Okay, another recap then. The LIA intensified pre-existing vulnerabilities, leading to terrible consequences like increased mortality, famine, and epidemics like the Black Death. It fueled social unrest, contributed to conflicts and state collapse like the Ming Dynasty, and even spurred irrational responses like the peak of the witch hunts. But societies weren't passive victims. They adapted through agricultural shifts, expanding trade networks became crucial buffers, and new economic activities like whaling emerged and innovated in response to the challenges. Land use changed. Resilience and ingenuity were also part of the story.
A complex picture of crisis and response.
Definitely. Now that we've explored these broader impacts and adaptations across Europe and beyond, let's zoom in on that specific, really fascinating case study you mentioned earlier, the Dutch Republic. Here was a society, a maritime power that seemingly thrived during the coldest part of the Little Ice Age. How did they manage that? All right, let's dive into the Dutch Republic, particularly during its golden age, which fascinatingly lines up almost perfectly with the coldest part of the Little Ice Age, roughly 1565 to 1720.
It's a remarkable coincidence, isn't it? During this period, when average European temperatures dropped by nearly a degree Celsius, the Dutch Republic experienced unprecedented economic prosperity, cultural flourishing, and political influence.
And they had this unique organic economy, right? Still heavily reliant on muscle power, wind, water, and peat as their main energy sources.
That's right. It wasn't industrial in the modern sense. Yet it supported high levels of urbanization, incredibly extensive networks of trade, thriving industrial centers producing goods like textiles and ships, and highly commercialized, efficient agriculture. Many historians see this as evidence of an unusually effective energy and transport system for its time.
So how did the system, so dependent on things like wind and water, cope with the challenges of the LIA, like colder winters and potentially more storms, especially their transport network?
That's the key question. The Dutch system was heavily reliant on waterborne transport, especially its dense network of canals and rivers. These were the most efficient conduits for moving people, goods, and information.
Sailboats, mostly.
Initially, yes, but increasingly they were supplemented, especially for passengers and reliable freight, by the famous trekvaart system.
Ah, the horse-drawn barges.
Exactly. These barges were pulled along canals by horses walking on towpaths. This made them far less susceptible to the whims of wind compared to sailboats. They offered regular, scheduled services between towns, a kind of early public transport system.
But still vulnerable to the weather in other ways.
Oh, yes. They were still vulnerable to severe storms, which could damage the canals or barges. And crucially, they were highly vulnerable to ice. When the canals froze solid, the trekvaart system ground to a halt.
What about roads? Did they have alternatives?
They did have road networks, particularly connecting inland areas. But in the coastal provinces, where most of the population and economic activity was concentrated, water transport absolutely dominated. Roads were often poorly maintained and could be rendered muddy and impassable by heavy rain or blocked by snowfall in winter.
So water was king, but vulnerable to freezing. How significant was the impact of ice on this critical transport system?
It was profound, especially during the severe winters of the LIA minima, like the Maunder minimum. We have direct evidence from records like the sound toll registers.
Those recorded ships passing between the North Sea and the Baltic?
Yes, and during the particularly frigid winter of 1694-95, the registers show a complete cessation of shipping through the Sound for months, from January basically through March, with sustained traffic only resuming in April.
Why? Too much ice.
Unusually extensive sea ice, stimulated by the sustained freezing conditions across northern Europe, it simply blocked the passage. And it wasn't just the Sound. Major rivers across Europe, like the Thames in London and the Elbe in Germany, also froze solid frequently during LIA winters.
And within the Dutch Republic itself?
Same story. We have records showing that the States General, the main governing body, couldn't even assemble in The Hague in January 1637 because the sustained freezing had stopped all the Bergveer traffic, the scheduled barge services that delegates relied on to travel.
So government business literally stopped.
It was significantly disrupted, and this had direct economic consequences. River tolls, a major source of income for towns, plummeted during these freeze-ups, impacting municipal finances.
How long could the canals be frozen?
During really severe winters, like 1662-63, or the infamous winter of 1683-84, records suggest the main Trekvaart routes could be halted for over 80 days, more than 2.5 months with no barge traffic.
Wow. How did people cope? How did goods still move?
They adapted. Milk boats, vital for supplying cities, faced peril from storms at sea, but when the waterways froze, farmers used sleds to transport milk and other produce over the ice into the cities. Brewers, who needed vast amounts of fresh water, invested in icebreakers or hired laborers to manually break the ice on canals to maintain their supply.
So the ice created immense challenges, but it also opened up new modes of transport, didn't it? You see all this famous Dutch winter painting?
Exactly. Skating and sledding became incredibly common. The frozen canals and rivers weren't just obstacles. They transformed into vibrant social spaces and transport corridors. People used skates and sleds for speedy movement, for commuting, for sport, for socializing. It was a remarkable cultural adaptation, turning inconvenience into a distinct feature of winter life, beautifully captured by artists like Hendrik Everkamp.
Though presumably traveling on the ice had its own dangers.
Oh, certainly. The ice could be unpredictable, especially during thawing and refreezing periods. Accidents were common. But it offered mobility when other options failed.
Interesting, too. You mentioned that during milder, drier periods within the LIA, lower water levels could also hinder boat traffic.
Yes, there's an interesting record from the summer of 1707, a milder period, where low water levels prompted people to travel overland using mules through former creeks and ditches that were usually navigable. It suggests that land travel might have become more important during warmer, drier phases of the LIA when water levels dropped. It shows adaptability in both directions.
Fascinating how they navigated those challenges. Now, beyond domestic travel and trade, the LIA also profoundly impacted European exploration, didn't it? Especially that elusive quest for a northeast passage to Asia. Tell us about the Dutch Arctic expeditions during this time.
All right, let's unpack this. The LIA, particularly its colder phases, like the Grindelwald fluctuation in the late 16th century, made conditions for Arctic exploration hardly auspicious, to quote one source. Sea ice was a constant, often insurmountable obstacle.
And the Dutch were major players in trying to find that northern route.
They were very keen. Finding a route north of Eurasia to reach Asia would bypass the Portuguese and Spanish monopolies on the southern routes. So they sponsored several key expeditions between 1594 and 1597, led by figures like Cornelis Ney, Cornelis Rip, and those famous Willem Barents.
How did those first voyages go, 1594, 1595?
They faced immediate difficulties. In 1594, Ney and Rip were imperiled by massive icebergs and thick fog, forcing them to turn back. Barents, exploring a different area, was thwarted by impassable sea ice further north. In 1595, Barents sailed again with a larger fleet, but got blocked by ice in the Karo Sea, east of Novaya Zemlya. Local Russian accounts warned them the sea would soon freeze solid right onto its southern coast. Faced with an overwhelming abundance of ice, they were forced to retreat again.
So, ice stopped them cold, literally. But the 1596 expedition is the truly legendary one, isn't it? The one where Barents and his crew got trapped and had to overwinter.
It is. This is one of the great survival stories in Arctic exploration history. Sailing again in 1596, Barents' ship, under his command, alongside Jacob van Heemskerk, became hopelessly trapped in the pack ice off the northeastern coast of Novaya Zemlya in late August.
Trapped for the winter.
Yes. By September 11th, it was obvious they weren't getting out. They faced the prospect of spending the entire Arctic winter, including months of total darkness, in this incredibly forbidding environment.
What did they do?
They salvaged timber from their trapped ship and, remarkably, managed to build a sturdy lodge on the shore, the famous saved house, or Het Behouden Huis. They endured incredible hardship, extreme cold, polar bear attacks, dwindling supplies, sickness like scurvy. The sun completely vanished below the horizon from early November until late January.
How many survived?
Only 12 of the original 17 men made it through the winter. When the ice finally began to break up in June 1597, they had to abandon their crushed ship and attempt to sail south in two small open boats salvaged from the wreck. Tragically, Willem Barents himself died during this perilous journey back.
An incredible ordeal. But did it achieve anything beyond the human drama?
Well, it definitively proved how harsh the Arctic winter was and effectively ended hopes of finding an easy northeast passage for centuries. But the detailed account of their survival, published later, revolutionized European understanding of the North. It led to much more accurate maps, replacing mythical lands and monsters with realistic depictions of ice and land.
And were there any unintended consequences, like with the whaling?
Yes. Crucially, during their voyages, particularly the earlier ones exploring westwards, Barents and his crews had charted the Svalbard archipelago, previously unknown or unclear to Europeans.
Svalbard, that became important for whaling, right?
Hugely important. The reports brought back about Svalbard's natural abundance, especially the vast numbers of whales sighted in its waters, directly inspired the first Dutch and English whaling expeditions there, starting around 1600. So while the quest for the passage failed, it inadvertently opened up a major new economic frontier, Arctic whaling, that became incredibly important, especially during the colder LIA period, another example of adaptation and finding opportunity amidst challenge.
Amazing. So the LAA-shaped exploration led to new industries. But what about the established giants of global trade? Were even powerful entities like the VOC, the Dutch East India Company, immune to the climate's influence?
Not at all. The VOC, despite being arguably the most powerful corporation in the world at the time, was profoundly affected by the LIA climate, both positively and negatively.
How so? We talked about potentially more storms. Did that impact their ships?
Yes, the evidence from VOC records ships' logs, day registers kept at outposts, correspondence strongly suggests that shipwrecks and mortality rates on their voyages both increased during periods with more frequent or severe storms, particularly in the North Sea region and around the Cape of Good Hope.
They actually tracked this.
They kept meticulous records. We can see spikes in mortality recorded in the day. Registers for voyages heading to Asia, often coinciding with reports of severe storms encountered shortly after leaving port. Correspondence sent back from Batavia, modern Jakarta, also shows fluctuations in how often storms were mentioned, with a notable peak around 1713-1724, right in the middle of the Maunder minimum.
Were their big ships vulnerable?
Their large East Indiamen were generally very seaworthy for the time. They were less likely to be sunk outright by gales compared to smaller merchant vessels like flutes or yachts. However, storms could still cause significant damage, delays, dismasting, loss of cargo, and increased wear and tear, contributing to higher costs and risks.
Did the LAA's climate also affect things like how long the voyages took? Changes in wind patterns, maybe?
Yes, absolutely. This is where the ship logbooks provide incredibly detailed meteorological data. During the Maunder minimum, for example, there seems to have been a noticeable rise in easterly winds in the North Sea region compared to other periods.
Easterly winds. How would that affect VOC ships leaving Holland for Asia?
It would likely have helped them on their outbound journey. Easterly winds would give them a favorable push down the English Channel and out into the Atlantic. So more frequent easterlies and perhaps more frequent storms coming from the north or east might have actually accelerated outbound VOC vessels on the first leg of their voyage.
So a potential upside to the LAA climate for the VOC, faster trips out.
Potentially, yes. Despite the increased storminess and risk, analysis of VOC journey times shows that the average time at sea for voyages from the Netherlands to the Cape and then on to Batavia actually declined gradually over the course of the 17th century.
Declined, even with the LIA deepening.
Yes. This suggests that other factors were likely more dominant in determining overall voyage length. Things like technological advancements in shipbuilding and navigation, better knowledge of winds and currents, and crucially, route optimization, like the adoption of the Brouwer Route, which used the strong westerly winds of the Southern Ocean to speed up the Indian Ocean, crossing likely offset or outweighed the climatic challenges.
So they adapted their routes and technology. What about the return journey from Batavia back to Europe?
That's interesting. The data there suggests that inbound journey times from Batavia back to the Netherlands actually increased by about 10% from the early days of the VOC to the end of the Maunder minimum.
Increased. Why would that be? Did the winds hinder them coming back?
It's possible, but the analysis suggests this increase might be more related to changes in the company's operational patterns, like ships making more secondary stops in Asia on the way home, rather than being solely driven by weather patterns. It's complex to disentangle all the factors.
Okay, so faced with these very specific climatic challenges, more storms, changing winds, ice, how did the Dutch, particularly the merchants in the VOC, actually respond?
They responded creatively and pragmatically. As we saw with journey times, they adapted routes and likely ship designs over time. They also developed sophisticated systems of maritime insurance to manage the increased risks. Their flexibility was key.
And what about trade closer to home, like the Baltic trade? That was vital for grain and timber, right?
Absolutely vital. And it was also significantly affected. As we saw with the Sound Toll records, lengthier winter freezing frequently prohibited travel through the Danish Straits into the Baltic, sometimes trapping ships in icy harbors for months. And the more common storms during LIA minima were often deadly to the less seaworthy bulk-carrying ships like flutes typically used in that trade. The Sound Toll data clearly show significant declines in traffic during the coldest periods.
So even this critical lifeline was vulnerable.
It was. Yet the Dutch economy overall proved remarkably resilient. It highlights their adaptability, their diverse trade networks, and perhaps their ability to manage risk and find alternative solutions when one road or sector faced challenges.
Okay, let's try to sum up this Dutch case study so far. The Dutch Republic, highly urbanized, commerce-dependent, operating an organic economy.
Displayed remarkable resilience during the LIA's coldest phases, its golden age coinciding with the climatic downturn.
Its extensive transportation networks, canals, trick-fart, roads, even adapting to use ice allowed for mobility and trade despite freezing and storms.
Arctic expeditions, driven by the quest for a northeast passage, failed in that goal due to LIA ice, but inadvertently led to crucial geographical discoveries like Svalbard and spurred the lucrative whaling industry.
And the mighty VOC, while facing increased storminess, mortality risks, and climate-influenced changes in journey times.
Adapted through navigational improvements, route optimization, likely technological tweaks, and flexible trade strategies, demonstrating how climate stress could drive innovation even within large established organizations.
It's a powerful story of adaptation. Now, from the challenges of trade and exploration, let's turn to the brutal reality of conflict during this period. Let's explore how the Little Ice Age climate profoundly shaped the Anglo-Dutch Wars. Okay, the Anglo-Dutch Wars. These were defining naval conflicts of the 17th century, fought largely in the North Sea, right in the heart of where the LIA was having significant impacts. This raises a really important question. How did the climate actually influence warfare back then? Especially naval battles so utterly dependent on the wind.
It's a critical factor, often overlooked in purely military histories. The LIA's climatic conditions, the temperature, the storminess, and especially the prevailing wind patterns had a direct and sometimes decisive impact on military operations, both on land and particularly at sea.
How did the two sides stack up navally, England versus the Dutch Republic?
They had different strengths. The English, particularly after the Commonwealth period, developed a revolutionary naval system. They built large, powerful warships, floating castles, with deep drafts and heavy artillery, designed for line-of-battle tactics.
And the Dutch?
The Dutch generally had smaller, shallower draft warships, partly dictated by the shallow waters around their coasts. But they possessed unparalleled collective knowledge of the complex North Sea environment, the tides, the sandbanks, the winds. Their tactics often emphasized maneuverability, grappling, boarding, and firing at the enemy's rigging to disable them, rather than just hull-smashing firepower. This local environmental knowledge became a crucial asymmetric advantage.
So how did specific LIA weather play out in the First Anglo-Dutch War, 1652 to 54?
We see it influencing battles right from the start. Take the Battle of Dover in May 1652. The Dutch fleet under Martin Tromp, burdened with convoy duty, was driven toward the English coast near Dover by a severe storm with strong north-northeast winds. This forced them into a defensive posture against the waiting English fleet.
So the wind dictated their position.
Absolutely. Or look at the Battle of Plymouth in August 1652. Intense westerly winds actually pushed one Dutch commander, De With, away from his intended destination, but at the same time, it hurried Tromp's fleet directly towards the English. It shows how the same wind could help one fleet while hindering another, depending on their location and objective.
It's like a chaotic chess game where the board keeps tilting.
A good way to put it. Then at the Battle of Dungeness in December 1652, a furious northwesterly gale put the Dutch fleet dangerously close to a lee shore, meaning the wind was blowing them towards land, making retreat difficult and maneuvering hazardous. This same wind, however, allowed the English fleet under Blake to seize the crucial weather gauge.
The weather gauge, that's the upwind position, right? Why was that so important?
Hugely important in the age of sail. Being upwind gave you the tactical initiative. You could choose when and how to engage, you weren't blinded by your own cannon smoke, and you could bear down on the enemy more easily. The Dutch, pinned against the coast, were at a disadvantage. The influence of these specific weather patterns, like the direction and strength of the wind, directly shaped the battles and could grant significant tactical advantages.
Fascinating how literally the breeze dictated the flow of battle. Now, moving forward to the Second Anglo-Dutch War, 1664-67, this occurred deeper into the LAA during a generally colder and stormier period, right?
Yes, this period saw notably cold temperatures, increased precipitation, a tendency towards more easterly winds, and enhanced storminess compared to the long-term average. And these conditions directly affected military readiness and strategy.
How so? Did the cold winters impact preparations?
Definitely. Severe winters, like the one in 64-65, significantly slowed down work in the shipyards. Timber could freeze. Workers couldn't operate effectively, delaying fleet preparation on both sides.
And the changing wind patterns, you mentioned more easterlies.
That was crucial. The source material suggests that change patterns of prevailing wind during this war often allowed the Republic's fleets to leave their ports more easily than usual. And those persistent easterlies, which were more common during this phase of the LIA.
They had consequences beyond just sailing.
Oh, yes. They directly aided Dutch privateers raiding English shipping in the North Sea. And devastatingly for England, strong easterly winds fanned the catastrophic Great Fire of London in September 1666, hindering efforts to control it.
Wow, the LIA fanning the flames of London.
It seems so. And those same easterlies were instrumental in the success of the audacious Dutch raid on the Medway in June 1667.
The raid where the Dutch sailed right up the Thames estuary and attacked the English fleet at anchor.
Exactly. Persistent easterly winds allowed Admiral de Ruyter's fleet to navigate the complex channels of the Medway, catch the English completely unprepared, burn several of their best ships, and tow away the English flagship, the Royal Charles, as a prize. It was a stunning victory for the Dutch and a humiliating, financially crippling blow for England, directly facilitated by the prevailing LIA winds.
Incredible. What about major battles during this war? Did wind play a role there too?
Absolutely. The 4 Days Battle in June 1666, one of the longest and bloodiest naval battles in history, saw shifting winds dramatically influence the fighting. The wind initially favored one side, then shifted, changing the tactical situation entirely. It showcased how volatile the conditions could be, and the Dutch ultimately won a decisive, though costly, victory.
So the weather was a constant, unpredictable player.
A major player. Conversely, just a couple of months later, in August 1666, a relentless stretch of easterly winds enabled the English Admiral Robert Holmes to sail into a Dutch anchorage and burn around 160 merchant vessels, an event known as Holmes' Bonfire. A catastrophe for Dutch trade, again directly enabled by specific wind patterns linked to the LIA climate.
It really underscores how dependent they were on favorable winds.
Okay.
Finally, the Third Anglo-Dutch War, 1672-73. This was the infamous Rampjar, the year of disaster for the Dutch, wasn't it? Invaded by France, England, and German states simultaneously. How did the climate of the Maunder Minimum influence this critical period?
The weather in 1672-73 definitely reflected the generally colder, wetter, and stormier conditions associated with the Maunder Minimum, and it played a complex role in the conflict.
Starting with the French invasion in 1672.
Yes. The initial French advance was actually delayed by a frigid winter and a late cold spring, which hampered their preparations and mobilization. However, this was followed by an unusually dry late spring and early summer.
Dry, how did that affect things?
It meant that the major rivers, like the Rhine, were unusually shallow. This allowed Louis XIV's massive army, with its 25,000 horses and 1,000 cannons forces that would normally have been bogged down in mud during a typical wet spring, to advance rapidly into Dutch territory. Contemporary paintings even depict the French cavalry wading easily across the shallow Rhine, bypassing key Dutch defenses.
So the initial LIA conditions helped the invaders.
Paradoxically, yes, the dryness did, but then the Dutch played their famous trump card, the Hollandic water line, waterlinie.
Right, deliberately flooding the land to create a defensive barrier.
Exactly. They opened the sluices and flooded vast swaths of low-lying land around the core province of Holland, creating a wide, shallow lake impassable to armies.
And how did the Maunder Minimum climate help that?
Because after the initial dry spell, the weather turned. Torrential rains and sustained cooling set in, typical of the Maunder Minimum summers. This deluge kept the flooded lands inundated and strengthened the waterline defense. The floods were so extensive they reportedly drowned as many as 2,000 troops from the Bishop of Munster's army who were allied with France.
Wow, drowned by the defenses.
And then, as winter approached, the LIA conditions created further challenges for the invaders. Periods of alternating freezing and thawing made the flooded waterline treacherous. The ice was often too thin to support troops and artillery trying to cross, but too thick to allow Dutch boats to maneuver for defense. It effectively stalled the Franco Alliance invasion and saved the heartland of the Republic.
So the Dutch strategically used the LIA's weather, the rain, the cold, the ice to their advantage.
Precisely. It's a remarkable example of strategic adaptation, leveraging the prevailing environmental conditions, harsh as they were, for military defense. The naval engagements during this war were also heavily influenced by LIA wind patterns, with easterlies often favoring Dutch tactics.
Okay, let's recap the wars. The Anglo-Dutch Wars, fought during the LIA, were significantly shaped by the climate.
Prevailing winds, increased storminess, severe cold, they affected naval strategy, ship construction, campaign timing, and the outcomes of battles.
Specific weather events offered tactical advantages, easterlies helping Dutch raids like the Medway, or hindering fleets pinned against a lee shore.
But the overall LIA regime forced both sides to adapt constantly, and the Dutch, facing existential threat during the Ramjar, masterfully leveraged the LIA's typical weather, the heavy rains and winter cold, to make their waterline defense incredibly effective, ultimately saving the Republic.
A powerful demonstration of adapting to, and even weaponizing, the climate. We've explored the material impacts of the LIA on agriculture, trade, exploration, conflict. Now, let's turn inwards and explore how people made sense of these profound environmental changes. Let's delve into the cultural responses and the human understanding of climate itself during this turbulent period. #tag cultural responses and the human understanding of climate. So, we've seen how the Little Ice Age dramatically affected life in very practical ways. But how did people living through it, particularly in a relatively educated society like the Dutch Republic, actually understand what was happening with the weather? Was it seen as just bad luck, divine punishment, or was there a more scientific understanding emerging?
That's a great question, and the answer is complex and divided. Let's unpack this. The Dutch understanding of weather during the LIA wasn't monolithic. It was a fascinating mix, often varying along social and educational lines. It was a society caught between an older worldview and the dawn of scientific inquiry.
What was the older view?
Well, you still had remnants of the pre-Copernican Aristotelian cosmology. This view saw the elements earth, water, air, fire circulating in spheres between the Earth and the Moon. Meteorological phenomena, including things we'd now consider astronomical like comets or meteors, were often lumped together as weather, originating within this sublunar sphere.
And this was being challenged.
Yes, because the LIA coincided precisely with the scientific revolution, and the Dutch Republic was a major center of this revolution. Thinkers like René Descartes, who actually lived and worked in the Republic for many years, were attempting to create new mechanistic explanations for natural phenomena, including weather.
Descartes wrote about meteorology.
He did. His theoretical explanations, based on particles and motion, were ultimately incorrect in their details, but they represented a huge shift towards seeking rational, naturalistic causes for weather, moving away from purely supernatural interpretations. His work was highly influential.
And new tools were emerging too, right?
Crucially, yes. We mentioned the invention of the thermometer by Fahrenheit in 1714, allowing quantitative measurement of temperature. And even earlier, the compound microscope, significantly improved based on Dutch innovations in lens grinding, was used by figures like Robert Hooke in England in 1665 to study the intricate geometric structures of snowflakes.
Studying snowflakes scientifically.
Exactly. These new instruments help bring weather phenomena into the realm of the rational, the orderly, the measurable, the quantifiable. People also started using clocks more systematically to record the timing and duration of weather events.
But despite these scientific strides, did people still cling to supernatural interpretations, especially when faced with devastating storms or failed harvests?
Oh, absolutely. Belief in divine intervention, or increasingly demonic influence as a cause for extreme weather, remained very common across all levels of society.
Divine intervention, like seeing good weather as a blessing.
Yes, or seeing storms as punishment. Certain events were widely interpreted as direct signs of Almighty God's will. A famous example, though slightly earlier, was the storm that devastated the Spanish Armada in 1588, celebrated in England and the Netherlands as the Protestant wind, a sign of divine favor. There are other accounts of sudden frosts arriving just as truces were signed, interpreted as God endorsing the peace.
And the flip side, demonic causes, linked to the witch hunts.
Yes, the belief that demons acting through witches could manipulate the weather seems to have grown stronger during the LIA's harshest periods. As we discussed, accused witches were frequently blamed for conjuring storms, causing frosts, blighting crops, and driving up grain prices through malevolent magic.
Did the Dutch Republic have as intense witch hunts as, say, parts of Germany? You mentioned it might have been dampened somewhat.
The persecution certainly occurred in the Dutch provinces, but generally it seems to have been less intense and finished earlier than in some other parts of Europe. Some historians speculate that the relatively higher standard of living and perhaps the more ambiguous material impact of the LIA in the highly commercialized, trade-dependent republic might have dampened some of the desperation that fueled the most extreme witch panics elsewhere. It's debated, but the connection between climate stress and witch hunts is strong in many regions.
So, a real mix of emerging science, traditional religious views, and outright superstition. How did this play out in everyday understanding? Did people lean one way or the other?
It seems to have been a blend, often coexisting. Looking at personal correspondence from the time, letters written by educated Dutch citizens, like government officials, sometimes show a more pragmatic approach. They might describe gales, floods, or ice in detail, focusing on the practical consequences, travel disruptions, damage to property without necessarily invoking divine or demonic agency.
Just reporting the facts.
More or less. But even then, you might find references to God's providence elsewhere in their writings. What's also fascinating is looking at letters dictated by illiterate but urban Dutch citizens, perhaps sailors on warships writing home.
What did they say about the weather?
Often their accounts reflect a very pragmatic, dispassionate approach. They focus on the immediate consequences of the weather, damage to the ship, delays, dangers faced, rather than speculating on the ultimate causes, whether natural or supernatural. Their primary concern seems to have been survival and coping with the conditions they faced. It highlights perhaps a different kind of understanding rooted in direct experience and adaptation rather than abstract explanation.
That makes sense. Focus on what you can control or react to. Now, how did ordinary people perceive shifts in weather over longer periods? Did they have a sense that the climate itself was changing, not just experiencing a bad winter or two? Did they have a concept of climate change without the modern term?
That's a tricky question. They certainly didn't have the global perspective or the scientific framework we have today. But they did seem to possess a limited yet significant awareness that prevailing meteorological conditions had changed over time, primarily through memories of extreme weather events.
Relying on personal memory and maybe stories from elders?
Exactly. Oral tradition played a role. I remember winters used to be. And some written records also provided context. While systematic record-keeping was rare, some parish records in Europe, or more systematic observational records kept in places like China going back centuries, could offer reference points.
How did they use memory? Were there specific events people remembered?
Yes, people definitely remembered and commented on unprecedented or unusually severe events. For example, a writer in Amsterdam in 1664 described a severe ice storm where a layer of ice the thickness of an arm coated the trees, noting explicitly that nobody had ever seen the like before. Or a Londoner describing a tempest in 1652 as so violent as no man alive had seen the like in this age.
So these extreme events stood out.
They did. They were appreciated for their rarity and often served as chronological landmarks in popular memory. The year of the Great Frost, the river froze solid.
Did they use these memories to compare winters?
It seems so. The most common way people seemed to gauge the severity of past winters was through memories of extensive ice cover and its impact on mobility.
Like remembering when you could skate across a certain river.
Precisely. There's an account from the winter of 1620-21 where people noted that horse-drawn sleighs could travel over the frozen sea ice to reach North Sea islands like Terschelling and Ameland. And they specifically remarked that this hadn't been possible since the equally frigid winter of 1607-08, 13 years earlier.
That suggests a pretty decent collective memory for comparing winter severity.
It does suggest a rough accuracy, yes. Although it's important to remember that ice cover itself isn't a perfect proxy for temperature alone. It's also affected by wind, currents, snowfall, and local conditions. But it was a tangible, memorable indicator people used.
So what's fascinating here is that even without our modern scientific tools and global data,
Many literate Dutch observers, at least, were using their memories, comparing notes, maybe referencing some older records, to roughly discern that patterns of severe weather were unstable and perhaps changing over time. It shows a localized, practical understanding of climatic shifts, even if they couldn't articulate it as climate change in our sense.
this cultural understanding, this mix of science, superstition, and practical memory must have influenced artistic expression, too. How did the LIA manifest in Dutch art and maybe other everyday adaptations?
The LIA definitely inspired cultural change, and perhaps nowhere more visibly than in Dutch winter landscapes. This became a hugely popular genre of painting during the Golden Age.
Right, those paintings filled with skaters and sleds on frozen canals.
Exactly. Paintings by artists like Avercam, Van Goyen, Isaias van de Velde,
Hmm.
they portrayed these vibrant social spaces that emerged when the frozen waterways allowed skating, sledding, ice fishing, games, and general winter festivities.
So art reflecting life adapting to the cold.
Very much so. These paintings depicted characteristically Dutch landscapes and showed how daily life adapted, transforming the inconvenience and hardship of the cold into opportunities for social interaction, commerce, market stalls set up on the ice, and recreation. They celebrated a particular aspect of Dutch life shaped by the LIA climate.
But can we be sure the climate caused this art genre?
That's always complex. Discerning direct causal links between climate and artistic expression is inevitably speculative. Artists have their own motivations, patrons have demands, artistic conventions evolve. But the sheer proliferation and popularity of these winter scenes during the coldest phases of the LIA strongly suggested the connection, a cultural resonance with the lived experience of those harsh winters.
Beyond painting, were there other cultural shifts? Fashion, architecture.
Yes, historians point to broader changes in cultural expressions, perhaps subtle shifts in architecture towards better insulation or heating, changes in fashion, maybe favoring warmer clothing styles, and events like the celebratory frost fairs held on the frozen River Thames in London during severe winters are another example of cultural adaptation.
It seems the Dutch, in particular, had a distinctive approach, pragmatic, adaptive.
Yes. And what's fascinating, as one source suggests, is the potential correlation between this distinct Dutch approach to understanding and coping with weather, that pragmatic blend we discussed, and the society's remarkable economic and military adaptability during the LIA.
Implying that how a society thinks about climate influences how well it copes with climate.
That's the intriguing suggestion, that the understanding of weather and climate change among a society's citizens, whether scientific, pragmatic, or even superstitious, shapes their capacity to successfully adapt to climatic fluctuations in the physical world. It hints at a feedback loop where cultural perceptions influence real-world resilience and vice versa.
Okay, let's recap this fascinating chapter on cultural responses. During the LIA, Dutch society grappled with climate shifts through a complex mix.
A blend of emerging scientific inquiry, enduring supernatural beliefs, though maybe less intense witch hunts than elsewhere, and a practical, memory-based understanding of extreme weather and changing conditions.
This was reflected in their daily life adaptations, using frozen canals for transport and socializing, and in their cultural expressions, most famously the winter landscape paintings.
And all this suggests a potentially crucial link between a society's cultural perception of weather and its actual, practical capacity for resilience and adaptation in the face of environmental change.
What an incredible journey we've taken, diving deep into the medieval warm period and the Little Ice Age. It feels like we've covered so much ground. We started by unpacking that often oversimplified argument about the medieval warm period, didn't we? We revealed its regional nature, not uniform global warmth.
And crucially, highlighted the importance of the rate of climatic change back then, which was significantly slower than what we're experiencing today, a factor often missed in modern comparisons.
We then plunged into the Little Ice Age, this extended period of widespread, though again regionally varied, cooling.
Exploring its complex origins, that interplay of natural forces like lower solar activity, more volcanic eruptions, shifts in ocean currents.
And potentially even that unintended human influence through massive reforestation in the Americas after the Great Dying, a really startling idea.
It is. And we saw how the LIA climate often acted as a potent threat multiplier.
Right, intensifying pre-existing societal vulnerabilities, leading to horrific outcomes like famine, increased susceptibility to devastating epidemics like the Black Death and the Plague of Justinian.
And contributing to profound political unrest, conflicts like the 30 Years' War, the collapse of the Ming Dynasty in China, and even fueling irrational fears that manifested in the surge of systematic witch hunts.
A bleak picture in many ways. However, if we connect this to the bigger picture, the story isn't just one of suffering and collapse.
Not at all. These historical periods also powerfully demonstrate remarkable human resilience and adaptation.
And the Dutch Republic, thriving during the LIA's nadir, really showcases this. Their flexible transportation networks adapting to ice, their innovative whaling industry spurred by Arctic challenges, their ingenious tactical adaptations during the Anglo-Dutch Wars, especially using the waterline.
All demonstrates how societies can adapt, innovate, and sometimes even find ways to thrive amidst significant climatic challenges.
And finally, we explored that fascinating dimension of how people perceived and understood the weather, that mix of early science, enduring supernatural beliefs, and practical popular memory.
and how those perceptions likely played a role in shaping their capacity to adapt, suggesting a link between cultural understanding and societal resilience.
So, looking back at this whole historical trajectory, what are the big takeaways? What relevance does understanding the MWP and LIA have for us today?
Well, I think it offers critical insights into that complex, reciprocal relationship between climate and human civilization. History shows us unequivocally that climate is not just a backdrop, it's an active force shaping human affairs. Now, obviously, the causes and especially the speed of past climate shifts, like the LIA driven by natural factors, differ fundamentally from today's human-induced climate change driven by greenhouse gas emissions. We absolutely cannot draw direct one-to-one parallels in terms of cause or solution.
That's a crucial caveat.
Absolutely critical. However, the historical record does provide profound lessons about vulnerability and resilience that remain highly relevant.
In what ways? Are modern societies more or less vulnerable?
It's complex. Modern societies are vastly larger, technologically advanced, better resourced in many ways, and globally interconnected. That offers certain advantages. But we're also arguably less flexible in some respects, highly dependent on complex, vulnerable infrastructure, incredibly densely populated, especially in coastal areas, and our interconnectedness means shocks can propagate globally very quickly. So we have new vulnerabilities alongside our strengths.
And what about the types of threats? History seems to point strongly towards food security.
Yes, the historical record is stark on this point. The drought-famine-starvation nexus, as some researchers call it, has been the main recurring serious threat to human health and survival, linked to climate variability across millennia. And while modern agriculture is vastly more productive, it's also highly optimized for current climate conditions and relies on complex supply chains, making it potentially vulnerable to disruption. The econometric analyses we touched on, while showing complex links between temperature and overall GDP, consistently find a strongly robust causal relationship between climate variables and agricultural output, yields, production, prices.
And that economic stress from agriculture can spill over?
It can. History suggests that climate-induced economic crises, food price spikes, resource scarcity can trigger or exacerbate social disturbances, riots, political instability, even wars, which can then feed back and worsen the initial crisis. Becomes a vicious cycle.
So the threat multiplier effect is still very relevant.
Very much so. And perhaps one final lesson, drawing from the Dutch experience in our discussion on cultural understanding.
Is that how we perceive and understand climate change today might influence our ability to effectively adapt.
Exactly. The Dutch example suggests that a society's collective understanding of weather and climate, whether it's informed by science, shaped by cultural narratives, or influenced by denial or misinformation, can profoundly impact its capacity and willingness to adapt proactively and effectively. It underscores the importance of climate literacy and open public discourse based on the best available evidence.
Impartially, then, this deep dive into past climates isn't about saying history repeats itself in a simple way or endorsing specific present-day actions.
Not at all. It's about using the rich tapestry of the past to inform our critical thinking about present-day challenges. To understand the deep, complex, and enduring influence of climate on human systems and the range of human responses from catastrophe to remarkable resilience.
So what does this all mean for you, our listener, a history enthusiast navigating today's world? Here's a final thought to consider. If past societies facing LA conditions with far fewer technological tools, no global communication network, and a limited scientific understanding of the Earth system, if they were still able in many cases to identify significant environmental shifts based on observation and memory, adapt their practices, innovate technologically, and sometimes even creatively benefit from the changes, what does that tell us about our own capacity for resilience, adaptation, and innovation today, facing the environmental changes of the 21st century, both those we anticipate and those that might still be unforeseen?